So before we get into the details of probabilistic graphical models, we need to talk a little bit about what a probability distribution is, just so we all have a shared vocabulary. So let's start with a very simple example of a joint distribution, one that is going to be extended in examples later on in other parts of the course. And let's start with an example that involves just 3 random variables. This is what I call the student example, and you have a student who can be described in this case by a variable representing his intelligence, and that could be high or low. The student is taking a class. The class might be difficult or not, so this random variable so the random variable I has 2 values, difficulty variable also has 2 values, and then there's the grade that the student gets in the course, and that has 3 values. In this case, we're going to assume A, B, and C. Now here's an example joint distribution over this set of 3 random variables. So this is an example of P of I comma D comma G. It's a joint distribution. And let's think about how many entries are in such a joint distribution. Well, since we have 3 variables and we need to represent the probability of every combination of values for each of these 3 variables. And so we have 2 times 2 times 3 possible combinations for a total of 12 possible values that we need to assign a probability to. So there's 12 total parameters in this probability. And I'm going to introduce a notion of independent parameters, which we're going to talk about later as well. Independent parameters are parameters whose value is not completely determined by the values of other parameters. So in this case, because this thing is a probability distribution, we know that all of the numbers here on the right have to sum to 1. And therefore, if you tell me 11 out of the 12, I know what the 12th is. And so the number of independent parameters is 11. And we'll see that that's a useful notion later on when we start evaluating the relative expressive power of different probability distributions. What are things that we can do with probability distributions? Well, one important thing that we can do is condition the probability distribution on a particular observation. So for example, assume that we observed that the student got an A. And so we have now an assignment to the variable G, which is G1. And that immediately eliminates all possible assignments that are not consistent with my observation. So everything but the G1 observations. Okay? And so that gives me a reduced probability distribution. And so this is an operation that's called reduction. I've taken the probability distribution, I've reduced away stuff that is not consistent with what I observed. Now that by itself doesn't give me a probability distribution, because notice that these numbers no longer sum to 1, because they summed to 1 before I threw out a bunch of stuff. And so in order to get a probability distribution, what I do is I take this normalized measure, an indication. The word measure indicates that it's a form of distribution, but the fact that it's unnormalized means that it doesn't sum to 1, it doesn't normalize to 1. So this unnormalized measure, if we want to turn it into a probability distribution, the obvious thing to do is to normalize it. And so what we're going to do is we're going to take all of these entries, we're going to sum them up, and that's going to give us a number, which in this case is 0.447. And we can now divide each of these by 0.447, and that's going to give us a normalized distribution, which in this case corresponds to the probability of I comma D given G1. So that's a way of taking an unnormalized measure and turning it into a normalized probability distribution. We'll see that this operation is one of the more important ones that we were using throughout the course. Okay, the final operation that I'm going to talk about regarding probability distribution is the operation of marginalization. And that is an operation that takes a probability distribution over a larger subset of variables and produces a probability distribution over a subset of those. So in this case, we have a probability distribution over I and D. And we say we want to marginalize I, which means we're going to basically sum up, we're going to throw away I and going to restrict attention to D. And so what that does is, for example, if I want to compute the probability of D0, I'm going to add up both of the entries that have D0 associated with them, and that's the one corresponding to I0 and the one corresponding to I1. And that's the marginalization of this probability distribution.